Hello, everybody. Thank you for joining us. I'm Nicholas Sokratov. I'm Head of Developer Experience here at Uber. Today, we're going to be talking about serverless. It's quite a revolution that's happening right now in software development and cloud industries. And we'll be changing the software development practices pretty drastically in the upcoming years. It's my pleasure to introduce these speakers. I've been fortunate to work with both of them. And it's really hard to find more passionate and more knowledgeable people when it comes to serverless space. Shawn Burke is on the left, is staff engineer at Uber. He is leading our serverless project called Catalyst. And Ajay Nair, pardon me, is principal product manager at AWS Lambda. Shawn?
All right, thanks, Nikolai. All right, welcome to everybody. Thanks for coming out today. So today we're going to try and do something fun and unique, which is we're going to sort of do a comparison trade-off presentation about Catalyst, which is a serverless system we're building here inside of Uber, and the reigning champion of the space, AWS Lambda. Just to sort of think about different perspectives on this problem and some of the different types of solutions that people could build. So serverless is a hot word in the industry. A lot of people get hung up with the word serverless. It still has servers. We're not going to get into that today. But we think that serverless is an important trend because if you think about the pace of infrastructure and the way that infrastructure has been handled in IT for quite a few years has been a very constant march towards higher levels of abstraction. Not that many years ago, you had machines that were somewhere in the building of your company, and then you put those machines in somebody else's building. And then you started renting access to those machines in another person's building. And then you started maybe using a PaaS that abstracted you away from even how those machines were run. And then maybe you moved to containerization, which abstracted at another level. And now we're at another level, a code-only abstraction that people are calling serverless. And we think that's the important part about serverless. So thinking back to those other abstractions, PaaS, Platform as a Service, has been popular for many years. There's lots of PaaS out there. Heroku's an example. Thank you. Heroku's an example of a PaaS. Microsoft has a PaaS, lots of PaaS out there. Google App Engine is an example. Some of the shortcomings of those systems are that they're very constraining. There's a little set of problems that they don't handle well because they sort of define the universe of solutions that you can use. On the other end of the spectrum is CaaS, containerization as a service. And Amazon's got a containerization service. Google does, Microsoft does. In containers, you can do whatever you want, but they don't help you much with infrastructure. So you don't have limitations, but they don't really support you in terms of abstraction. So today we're talking about solutions in the serverless space, which are end-to-end platforms that are really focused on developers and making developers' lives better and easier. So why does Uber care about serverless? When I came to Uber about 1.5 years ago, my background is in developer tools. I worked at Microsoft Developer Tools for 15 years. I noticed how complicated things were for our developers in a lot of cases here. Our developers were spending a lot of time writing boilerplate code. They were spending time writing code to hook up to Kafka, writing code to hook up to our RPC services, or writing code just to basically manage logging and configuration and some other things. About that same time, I had been playing with AWS Lambda, and it was really clear to me that Lambda was the future of the internet. Like, this is the way that you want to write your code if you're a developer and you want to just get things done. So basically, I started looking at our use cases. Most of the developers here at Uber are writing code that you would recognize as an Uber product, whether it's UberX and the ride matching service, or some of our more specific services like Uber Family or Uber Airports. The code they're writing is very apt here. They take an endpoint from a mobile or a website. They do some munging on that. They call something from a database. Maybe they process a Kafka feed. And that's basically all they do. But they were spending a bunch of time messing with infrastructure. So I started thinking about how we could do it with a better model. And I started suggesting to management here that maybe we could do it in a serverless way. I managed to annoy the right people. And so we're building this product called Catalyst here at Uber. So since the serverless space has been really defined by AWS and AWS Lambda, Ajay has agreed to be here and talk today as well. And I'm going to hand it over to him for a minute.
I think we can kind of step up on the stage.
If you want to step on the stage, you can.
Yeah. All right. Let's see. All right. Thanks, Shawn. So, hi, folks. Ajay. I thought before we kind of go too far down the road, I thought we'll talk about sort of how we talk about serverless. Everyone's probably had the like Shawn said, the famous Twitter argument about no, it really has servers. Stories of wireless and by the way, the best analogy I've heard of this is Lambda is like Uber for compute, uh, in the sense that you only pay for when you're actually using it and you don't care about the car. So anyway, so coming for that, how we talk about serverless, we kind of talk about 4 criteria that needs to apply to anything to be called serverless, right? And what you'll notice is all of these are mirror images of responsibilities that you have when you're managing your own fleet of servers, right? First, simple but usable primitives. In the case of Lambda or many of these other sort of serverless compute offerings, code is all you deal with, code is all you manage. You don't have anything that looks like a container or a server. You don't muck around with CPU specifications or instance sizes or rack definitions or any of those things which typically you would have to do if you were managing your own fleet, right? Second, and I'm kind of going to go vertical down, is you never pay for idle. And this, by the way, is probably the strongest proponent or tenant that we have for serverless, in the sense that the biggest challenge we heard when customers were talking to us about solutions similar to, and by the way, Lambda started with a similar set of problems, which we heard from AWS customers around abstracting kind of the complexity for doing application development, was having to do capacity management, managing peak to average, figuring out exactly how much workloads can I carry so that I don't overpay for things that I'm not doing. When it comes to serverless solutions like Lambda and others, you never pay for idle, in the sense you're only paying for actual work done. In the case of Lambda, you pay in units of 100 milliseconds for the amount of time your code actually runs. And you can imagine kind of the cost savings that you get while moving over. For example, Nordstrom moved over an analytics system that does a few million transactions a day over. They've dropped their costs by about 2x. We had a publishing company in Singapore, which was doing they were spending about $30,000 on a custom image processing solution. They migrated over to using S3 and Lambda. Now their monthly bill is $123. So sort of magnitude of difference. We'll save questions for the end. We're here all night. Question? Yes. Yes, these slides will be available. Yes. Sure. Sorry, where was I? Never pay for idle. Benchling, but my new favorite example, they run CRISPR algorithms using Lambda on some of their genome data. They were spending multiple thousands of dollars per month. Their monthly bill is now 60. So these are like order of magnitude differences in cost, because you no longer have to worry about shaping your capacity to peak to average. Third, scales with usage. We talk about serverless being event-driven, request-driven, others. We'll talk about sort of FAS, or functions as a service, and the programming model that comes with it a little further. But the concept is it automatically has enough capacity to handle whatever work you're throwing at it. You don't have to worry about scaling as an activity. And last, but definitely not the least, availability and fault tolerance, things that you would typically manage for or structure for or have a dedicated team for to sit and manage availability zones, those are just built in. That's sort of a birthright, as we like to call it over here. And this, you can imagine, leads to heavy duty savings in your operations team. We have a company called Vidroll, which does video analytics and stuff. They use Lambda and Kinesis underneath the covers. They've scaled down or shifted their operations team from 10 people to 3 people and have all of them now building new stuff over there. So again, significant savings, not just monetary wise, but also people wise. A very related concept is sort of this functions as a service, so to speak, right? When it comes to serverless computing, there's a core programming model that it's kind of enforcing in order to kind of realize some of these benefits, in order for it to be event-driven, in order to us to allow you to pay as you go or never pay for idle. And we'll be spending a lot of our talk kind of focusing on elements of both solutions over here, both Catalyst and Lambda, that kind of embody some of this. As Shawn said, the goal is to make development as simple as possible for building applications, which means you want to keep some things exactly the same. You use the same languages that you prefer. You don't have to learn a brand new, Go. I don't want to say Goober, but that sounds like a weird language. But you don't want to learn like the special flavor of Go that Uber uses or anything of that. You want to use the same standard structures that you have. Second, you want to use the same deployment practices and others that you continue to use. You're already using Git for storing your code. You're already using Travis for doing your deployments. You want to kind of have that same development workflow going in place. You still want code quality and control, things that developers are good at, passionate about, and makes a difference to your application continues to be yours. Now, in order for us to realize some of this, though, there are some unique elements that get sort of baked into the architecture of a serverless application, if you will. And a lot of these are reflective of ideas that are already out there. People who are familiar with reactive programming or microservices or 12-factor apps, you'll see a lot of those concepts sort of embodied inside the platform, and the platform being opinionated about these. Things like your code is, your application is basically structured as events or things that emit and tell you when things happen. Functions, which are sort of code that you've written to take the action that you need to, one or more of them. And then the downstream services that they talk to. Could be data services, could be other API endpoints, and so on and so forth. And what's unique is everything in the system talks to each other through requests and events, right? There is no long living service that is listening for activity elsewhere. There's no sockets in play. Everything only reacts when something else is necessarily happening. So you have to plan for that, or you have to architect your system to keep that in mind. This also means lifting and shifting an existing app is not something that we would strongly probably recommend. You have to kind of think through what your serverless application looks like when you're moving it over here, right? Second, modular, which means because you're writing things as individual functions, you don't typically try to overload individual functions to do multiple things, right? Most of your developers in the audience, when you write functions do one thing and do one thing really well, right? And you want all of them to talk to each other through kind of these events and requests that are going on there. And finally, in order for us to kind of give you that promise of sort of scale automatically based on events, functions are typically stateless. Each code execution does not carry state with it. However, you're welcome to store state in external services like databases or others. So sort of the FAS tenants, if you will, or kind of concepts, as well as the serverless concepts, are something that will be typically embodied in both the services that you see over here, both with Lambda and with Catalyst. Yes, thank you. So again, just to give you kind of bringing back to Lambda, right? So the event sources that we support are kind of coming about, I want to say maybe 3 flavors, right? One is data stores that AWS already owns, or data stores within AWS, which allow you to react to changes in data, right? So we have an object store called S3, we have a database called DynamoDB, we have a stream store called Kinesis. You can react to changes in data stored in any of these. Second, we have a class where you can react to state changes. So if an instance gets created or an alarm goes off or a new log shows up somewhere, you can react to those changes and write functions to react to those. And third, and again, a very popular one, is sort of, bring your own event source, so to speak. And there's sort of 2 variants of this. One, if your service already speaks HTTP, typically services that have extensibilities as webhooks, you can use what we have a service called Amazon API Gateway that allows you to set up an HTTP bridge to your Lambda function. Or if you want to build your own event source, you got a system sitting inside your company that needs to invoke a Lambda function, you can just use our SDK for directly invoking a Lambda function that you have. Like an example for like kind of the latter bucket, Twilio allows you to use Lambda functions for kind of writing IVRs or voice apps for their particular service. Slack allows you to write bots using Lambda functions. Zapier is an example of someone who's used kind of an SDK to kind of bake it. Zapier is sort of IFT for enterprise applications, and they use Lambda to kind of power a lot of those integrations that happen underneath the covers. The functions themselves are, like we said, written in standard language stacks. Today, Lambda supports Node, Java, C#, Python. We'll talk a little bit about this further, but basically because of the fact that you can support arbitrary binaries and packaged along with your function, the number of languages people run in it are kind of crazy. I have had people running MATLAB, people running Fortran, and actually MATLAB was my favorite. I can't say any of the others are. And of course, Go shows up as kind of through a side door, and they run that inside Lambda. And finally, the idea is that you can communicate with any services. This is standard code. You bring in your own SDK. You can talk to an Uber API if the endpoint is available. You can talk to any of the AWS APIs. Lambda gives you the capability to secure these interactions in various forms and fashions. Not going to go too deep into that. We can talk about it after if you're interested in exactly what those look like. Quick kind of heads up on the various use cases that people see serverless being used for, right? And Shawn kind of brought this point up about this being focused on applications. And initially when we started out, we had a few app classes in mind. We had heard people doing big data processing coming to us and saying the event-driven model fits in really well. Basically interactive microservices, API endpoints, Lambda functions fitting in really well. But over time, at least in the last sort of 2 years that Lambda has been generally available, we have seen this grow really rapidly, right? So web apps, think about how you write a web app. Today with Lambda, a web app basically becomes a static page stored in S3 backed by a microservice using API Gateway and Lambda, and that's it. right? We had a pretty famous online video provider who has a series about Thrones, basically come out to us and say, we want to build a marketing site on you, and we have to launch in kind of 2 days. And we basically spiked up to 55,000 TPS in 1 hour and back down. And it was fine. They had a great launch. The marketing site went well. And they come to us and they were like, well, we kind of had given you sort of 2x what our estimate of capacity was. And you guys were able to hand up kind of that without us even really realizing that that was a difference of what was going on. So the kind of scale behavior that you're getting for websites is radically different. Similar things with backends. So talk about connected devices backends, mobile backends, variety of use cases to go over there. I'm happy to kind of give you specific references and architectures for each one of those. There's just so much to cover there that I might just end up talking about that all the time. Data processing is probably a really big application for the patterns we talked about there, right? You can imagine reacting to data changes stored in S3, where you can build media applications like video transcoding, image thumbnailing, facial recognition. We actually put out recently a reference architecture that combines AWS recognition, which allows you to do image recognition technology or facial detection on it, and allows you to essentially build your own face detection app with a couple of clicks. Chatbots we talked about, integrations with Slack and others kind of help you do that. And I'll kind of call out the last one, which kind of speaks to a little bit of how Amazon itself is using Lambda in different ways, right? Similar to what probably Catalyst is doing for Uber, a lot of these efforts within Amazon, which were previously doing these one-off microservices or one-off data processors, or even kind of, and the big production ones are now starting to consolidate on Lambda because we are now offloading all those operational tasks for us. And a canonical example of this was Lambda being the engine that powers Alexa skills, right? So when you write a skill for Alexa, you're basically writing a Lambda function and then wiring it up to Alexa to react to those events, right? And autonomous IT tends to be a good warm-up use case for many people. All the DevOps folks offload all their Python scripts onto Lambda and sit back happily ever after. Lambda gives 1 million requests away for free every month as a free tier. And you can imagine not many operational scripts cross 1 million requests a month. So it's basically free operations without having the cost to go with it. Now I'll kind of bridge into how we write a handler. I want to kind of start doing the interplay between Catalyst and Lambda and how you'll see the programming model. So this is an example of a Python Lambda function. For those of you who are familiar with Python, it's standard Python, nothing complicated or no custom frameworks here. Literally the only thing that Lambda enforces in this is basically line 12 that says your method signature has to have 2 arguments, right? A context object and event object. If you are wiring it up to one of the sort of standard event sources that we support, the event structure is supplied by that particular event source, so S3 or Dynamo or Kinesis or so on. If you're doing custom, you can basically pass in an arbitrary JSON payload and that'll show up inside your function. The context object allows you to kind of interact with the runtime itself. So if you want to know how much more time do I have before I hit my timeout, or how much memory was my function allocated, or which log group am I going to go write information on, or if you were triggered through a mobile app, what was the user context which was passed down to me from that mobile app? All of that's available inside of the context object. And kind of re-stressing that point, you can pretty much bring any libraries that you want, including native ones. The only requirement is that it's compiled for a flavor of Linux that Amazon offers called Amazon Linux. All of that can be packaged and deployed as part of your deployment package. You will see an example of kind of the web backend using Node in one of our demos forward. So I'm not going to overstress on this, but the main thing I want to kind of highlight is standard Python. There's a structure that comes with it and kind of arbitrary libraries that go over there. Last but not the least, you'll see lines in there for logging statements like line 20, line 25. Standard logging comments, standard file system operations, all of those are supported inside Lambda, no such restrictions. Your logging statements flow into the log solution that we have, which we'll be talking about a little bit further. So with that kind of just set up about Lambda use cases and the handler, I'm going to give it to Shawn to kind of bridge that back to Catalyst.
All right, thank you. Okay, powerful stuff. So one question that we get quite a lot, or I get quite a lot, is how come you guys aren't just using AWS Lambda? Probably some folks out here wondering that. So the main reason is that Uber's not an AWS shop. We don't run our production workflows in AWS. We have some pretty tight latency requirements for our functions. More importantly, there's a level of visibility that we want into the system that is difficult with an external system. We want to be able to get metrics at the very, very minute layer of when things go through the process. So that's why we decided to build our own thing. Uber's probably the biggest Go shop in the world. We've made a big investment in Go here, and so Catalyst is written in Go, top to bottom. Catalyst will support other types of languages, but that's the key thing. The way infrastructure is done at Uber today is microservices. We've got a lot of them, a lot of them. And while they're fairly easy to create, there's still a lot of overhead in building a microservice here. You have to name it, you have to put an on-call on it, you have to go through some processes for provisioning. There's lots of cases where people just don't even need to bother with that. So the scenarios that we wanted to target were backends for mobile and web apps, I mentioned that, asynchronous message processing. But an important requirement for the system would be that we would have extensibility for future systems. If we integrate a workflow system, we want to be able to support workflow tasks and deciders in our Lambda system. Batch processing. So we want to make sure that anything that comes along in the future, we're able to support. So we designed a system for extensibility in the future. But our goals were really pretty simple. We wanted to radically simplify what it took to build customer-facing backends logic here at Uber. We wanted our developers to be 100% focused on business logic and not on managing infrastructure. So what that meant is that it's a very code-centric design. You start with your code and the tooling just does things for you automatically. We wanted to make sure that it was easy to write, test, and debug code. And so we're going to go into some examples of how we've made that really easy. And we wanted to make sure that it was infrastructure agnostic. What that means is that when we introduce Catalyst at Uber, we don't want to have to go around to every other service in the company and teach it about Catalyst. So we wanted to make something that was easy to integrate and so we could migrate to over time and not have to go and touch a whole bunch of different services. And then finally, we wanted to make sure it was very low overhead in terms of performance. If the message to our developers was, we've got this great new system, but you're going to incur 100 millisecond round trip cost every time there's a query, it's just not going to work. So we wanted to make a very, very performant system that we could trust at large scale. So let's take a look at what it means to write a handler for Catalyst in Go. We're going to be supporting some other languages as well, but today we're doing Go. So the first thing that I'll do here is I'm going to create a handler. It's a completely normal function. You'll notice, similar to what Ajay said, our handlers have this first thing here called a context. We'll talk more about that in a second. But then you can write any code you want here. Just like with AWS Lambda, you can use any libraries you want. Very few restrictions on the type of code that you can run. We'll talk about how that code is hosted in a little bit. So once you've written your handler code here, in Go, you need to also register that handler with the system. So in this case, we're doing a very simple HTTP handler. We've written our code there. It just returns a little smiley face. And we tell the system here that it's going to be at route /, so index the route, the base default route, and it's going to be a GET. That's all we need to tell the system. So the point of serverless here for us, similar to AWS, is that you write your code, you tell the system when to invoke it, it figures out the rest for you. So let's do another example in this same, while we're at it here. Let's do a Kafka handler. Same idea here, I create a handler function. I start with a context, and in this case, I'm gonna just have it pick up the raw bytes from Kafka. And then we're gonna do some logging of how long the message was, not that important. Same exact thing here, we're going to then tell the system to register that Kafka for that Kafka topic. That's it. The system has all the information it needs to now go ahead and figure out how to hook that up in production. So if I wanted to have a string instead of a byte array, because we're processing user code, we can do a bunch of smart things on behalf of the user. So what happened here was this originally was a byte array, now we changed it to a string. This tells our infrastructure that you actually want those bytes as a string, so we'll automatically take those bytes and make them a string for you. You don't have to worry about that marshalling. We support JSON and Avro marshalling as well. But the point is here is we do work on behalf of the developer based on hints they give us from their code. And then finally, we talked about this context here. And so this Catalyst context is an interface. And here's the stuff that's hanging off of it. So why this is important is this means the developer is not worrying about configuring logging, metrics, configuration, stuff like this. It just works. And the interfaces that we pass you in your handler are already set up for your handler. What that means is that when you do metrics from your handler, the metrics are already tagged with your handler name. When you do logging with your handler, the logger already has tags about what project you're in, other information like that. Configuration, we can set up configuration that's at a project or a handler level. It automatically overrides and that's already set up for you and sort of flattens. You just read it, it's all good to go. And then we support something called resources, which is if you want values to live outside of the scope of a handler, you want to initialize database connections or some cache data, we just hand it to you and you can use it there. So when you want to run your handlers, we have a really easy workstation-centric way for you to run your handlers at development time. We have a CLI, it's called Catalyst. You just type Catalyst run, and we're going to walk through what happens with that code on your local machine. So when you do Catalyst run, what happens is that we do a build process. We wrap the code that you gave us in some architecture so that we know how to invoke it. We inspect that code and we produce two things. One is we produce a worker binary, which is the actual executable that will be launched at runtime. And we create a thing called a manifest. And the manifest is the metadata that our system needs to know about that worker to know what's in there. And so here's an example of what ends up coming out of it, and we automatically produce all this. The point of this is that this manifest matches the code that we just wrote. So it tells the system that it's an HTTP source type here, and we'll talk about sources in a second. This one's a Kafka source type. You'll see that we have baked in some metadata around this. So this gives Catalyst everything it needs to know to now wire up your code in production or locally. And we'll do it locally in this example here. So what happens is that packages that are handed to our runtime component, it's a process that we call the nanny. Because really what nanny does is it manages a set of processes. So it's going to create a few processes. It's going to see your worker binary, it's going to create that, and it's going to see from that manifest that you need an HTTP source and need a Kafka source. And so what it does is it hooks all these guys up to each other. And then when it's ready to go, it starts accepting traffic. And it comes. So now you've got a working system that you can test. You can call your HTTP endpoints. You can start feeding Kafka streams at it. It just starts working. You can launch it in your debugger. It's all very natural to run locally. This section of components here, the nanny plus your worker plus the sources, in production, that's a container. So it's the exact same model. Those are your components that make up your system in production. The reason this is important is that once this thing is up and running in production, we have a shared nothing architecture. That means if the control plane for Catalyst explodes, your handlers continue to run completely happily. You might not be able to scale up or deploy new stuff. That's obviously bad, but your existing running stuff still runs just fine. So it's a shared nothing architecture. As far as the rest of the world is concerned, it has no idea that Catalyst did this for you. It looks just like a regular HTTP endpoint. It looks like a regular Kafka ingester. So it fits into infrastructure very well. So that's how we do deployment, or how we do runtime locally with Catalyst. So Lambda, how do you guys do it?
Local deployment. So Shawn brought up sort of a few great points and about kind of elements when it comes to your function. A lot of the architecture that Lambda actually employs under the covers is very similar, which is why we kind of didn't bother duplicating the whole thing. Lambda leverages containers underneath the covers for kind of doing a lot of the placement and scaling that we talked about over here. One of the interesting things that we do slightly differently, and I'll kind of just bridge into that, is along with your code, the config that you specify doesn't necessarily specify the event source mappings as you were talking about. That comes as a separate API. We kind of keep that separate. But what goes with the function, though, is elements such as name, description, security context, things like runtime, and all those kind of elements. And you'll see some of this in the demo that Brian and Rory at the back are going to do for you if they keep their beers up. Anyway, so going with our deployment tools, right? So the idea over here is to kind of keep the workflow as consistent as possible with something that you do today, right? Today, when you write code, you write your code. There's some kind of packaging or build step that happens, which brings in external dependencies, produces manifest files. There's some degree of testing, be it local or in the environment that you're actually going to push to. And then kind of you have the deploy action where it goes out, and then kind of do your rinse repeat over there, right? Lambda offers a few tools that do it for straightforward, simple cases. The console itself has an end-to-end support for this. There's an inline editor, kind of automatically packages and deploys your code, allows you to do testing inside the console itself, and then wire up event sources. Our IDE plugins for Java and C# for Eclipse and Visual Studio allow you to do local testing, do simulations of event sources over there, and deploy it. And then because sort of Lambda opens up the APIs, it's just standard AWS APIs that are available for both create and invoke. There's an ecosystem of third-party tools that are being built out there. You'll see some familiar names like Travis and CodeShip out there who are already supporting deployments to Lambda. And then there are frameworks like Serverless, Claudia, Apex, Sparta, by the way, which leverages kind of the shimming out capability of Lambda for kind of having a Go-based framework for deploying onto Lambda and API Gateway. All of these allow you to kind of build microservices and kind of doing packaging and deployment in a standard fashion. Oh, sorry, I left the clicker with you, didn't I? That's all, folks. So, so digging into a couple of more deeper concepts over here, right? So along with your function, a couple of things that Lambda supports is the concept of version. So any function that you deploy, you can publish an immutable copy of that code such that, which kind of guarantees its behavior for the client that's calling it. So imagine you published, say, something with a single smiley face, published a version of it, and you have an API endpoint pointing to it. That behavior will not change. You will not be able to override that code or change the config that goes with it. Along with versions, we also have a kind of a partner feature that goes with it called aliases that allows you to essentially specify a pointer to the version that you specified. So if you have a function foo, you can have an alias called foo:prod and point it to v1. And when you publish v2, you simply repoint alias prod to version 2, which now gives you automatic promotion or control promotions of your versions. By default, Lambda functions execute kind of the latest copy of the code that's out there, which works fine for many people. But aliases and versions kind of give you the ability to kind of do controlled upgrades of your functions as you move along. And aliases abstracts kind of that version thrash that you may or may not have from your consumers or clients or your event sources, be it Kafka, Kinesis, API Gateway, and others, right? Lambda also supports the construct of environment variables similar to what you would expect of an application that you're writing over here, which allows you to inject parameters such as downstream endpoints that you're hitting. It's encrypted by default. So if you have encrypted credentials that you want to store in there for accessing a store downstairs, all of those are viable things to put in. So at a function level, that all makes sense. But when we talk about an application, going back to kind of that diagram we had, you have event sources, multiple functions talking to multiple downstream services. And we kind of, in order to kind of address that problem, we introduced this thing called the AWS Serverless Application Model, affectionately known as SAM, along with a cute icon as well. The idea behind SAM is to give you a standard way to express a serverless application. Right. So if you look at kind of the specification here, it's probably a little smaller than I thought it would look. But the idea behind it is you can specify the resource, which is your function, right? Say that you basically give it a code URI where the package zip is available. So think about, say, the Python function that you're writing. Python plus the libraries zipped up is essentially a deployment package. And this acts as the manifest to tell us what the application looks like, right? So the manifest says, this is the location where my code is. This is the specific handler inside my function that I want to actually invoke. This is the runtime that goes with it. This is the security policy I want to apply to it, which dictates what access permissions it has inside AWS. And then you'll see kind of this mapping structure at the bottom, which tells what events are going to actually trigger that function. So what's an output of a build step for you becomes an input for a build step in the case of Lambda. And in this case, we've said any method of the API that I'm specifying, auto-generated based on the API name, can turn around and invoke this function. And you have similar constructs that go with it that say, Kinesis handlers or S3 handlers or Dynamo handlers and so on and so forth that goes. SAM is underneath powered by AWS CloudFormation. So AWS CloudFormation is a way for you to provision resources within AWS. It has powerful constructs around provisioning, rollback, kind of doing sequence updates and all those kind of elements that go with it. The fact, because you're using, because it leverages CloudFormation under the covers, you get kind of all the extensibility powers that come with CloudFormation to go with it. So not only can you do what we call serverless resources with this particular manifest, but pretty much any resource within AWS can be provisioned using this mechanism and deployed using this mechanism. Do I already have next? Okay, sorry. So one last element, and this will be covered more in the demo. The steps basically now involve, going back to kind of this graph, is you write your function, use your favorite IDE that you so choose. Package is basically, there's a package command that comes with the CloudFormation CLI that will automatically zip up the contents of your local file, upload it to an S3 bucket. Test means you can deploy it to a versioned alias that you may have that says that I want to test it against my test endpoint first. And then deploy would actually essentially be switching that alias to your prod alias and then having it go from there. And I know this sounds like a lot of words right now, but it'll become a lot more easier to understand when we kind of look at the demo. So switching over to Catalyst.
Thank you. Okay. Yeah, so it's good. I'm learning a lot about AWS Lambda while I'm here too. And it's good to see that that system has come to a lot of the same conclusions that we have. Some of the things that AWS Lambda is doing, we've patterned after. Versions and aliases, we call them stages, but we do the same thing. That allows people to roll out parallel deployments of the same logical code at different versions. So you could have a production one and a staging one, and they won't mess with each other. So we do something similar, which is great. So when it comes time to deploy with Catalyst, how does that work? Our same CLI again, you go to the directory of the code that you want to deploy, and we'll show this in a demo. So one thing to note is that you guys are seeing this before most people at Uber are. This is really fresh. We got this working last week. It's coming along very well. So that's cool. That's cool. So, so you basically go to your directory where your handlers are, say it's called Kafka Catalyst, and you say Catalyst build. So that builds the package. We already talked about that. Once the package is built, you can upload that package. And upload is something that we would expect to happen as part of your CI flow. You wouldn't expect developers to do this. So the flow we expect to happen is that a developer commits some code, a CI system runs that code, and if all the tests pass, it takes and calls this CLI and uploads it up to the Catalyst system. What this is basically doing is associating a Git SHA with a package that's sitting up inside the Catalyst system's storage. So we know about a set of code that we can deploy. So once upload has happened and the package is sitting up in the Catalyst system, we have a component that we call the registry, and that's basically the directory of all the things that Catalyst knows about. And so upload tells the registry about a new set of code, and then deploy is essentially how you tell Catalyst to actually go ahead and roll out a specific SHA, specific version of code, out into production. And so what you see here, -s dev, that's something we call stages. It's exactly the same concept that Ajay talked about with versions. So for the stage dev, we want to roll out this new component, this new build. And this -i3 here basically says we want to do it for 3 instances. We'll talk about scaling in a slide a little bit later. So we do that, and the registry now goes to the controller. So now we have another service called a controller, which registry says, hey, controller, there's some new stuff that I would like you to roll out. And so it basically hands those same manifests that we showed earlier, hand it to the controller, and the controller picks nannies, figures out which instances are available, and starts deploying the code to those nannies. So once those nannies are deployed from your command line, we can actually check the status of those deployments from the command line as well. We can see what's going on with those, make sure they're up and running. And so if I type Catalyst status -f, same stage again, I'll get some information that comes right back in my command line. In this case, it basically says that it deployed 3 boxes successfully. And here's the SHA they're at and what pod they're in and what the target SHA is. So that's basically how you can have a very command line developer experience focused flow around deploying stuff to Catalyst. So back to Lambda for scaling.
Scaling? Yes, all right, scaling. This is something that, just given how long we've been out there, something we've gotten kind of good at. My favorite example right now, this is FINRA was on stage at reInvent a couple of months ago. reInvent is a big AWS event, and they're doing 500 billion transactions a day using Lambda right now, right? So we're starting to hit some pretty high numbers in terms of how much traffic are people kind of running through serverless applications. And there's kind of 3 heuristics or models that we have for scaling over here, right? Now, keep in mind, one of the tenets we had called out for serverless is that we will automatically figure out how much we need to run your code or how many copies of your code we need to run based on the number of events that are coming in. But not all events are kind of created equal, right? So Lambda offers kind of 3 different invocation models, so to speak. One is our default one, most common one is kind of the asynchronous approach. You submit an event, we queue it underneath the covers, and then for each event or each event, we spin up an individual copy of your code, right, running in its own environment and running individually. So if you give 1 event, you'll get 1 copy. If you get 1,000 in 1 second, you'll get 1,000, a million, so on and so forth. This is the model that services like S3, SNS, or SNS is our pub sub service in AWS. All of them kind of use this approach. And this model works well when you're okay taking kind of that, when you're okay having that little bit of a slack in the middle of your operations, right? You get a huge surge of events. We automatically queue it under the covers. We take care of retries because of the fact that we are queuing it, and then automatically turn around and invoke your code. Specifically in the case of asynchronous systems, Lambda automatically retries any failed events for 3 times. This goes back again to the concept we were talking about, availability and reliability being built in. Because of the fact that we are handling the event flow that's coming in, we're able to kind of give you that construct of retries that goes with it. The synchronous model or the request response model is similar in the sense that we still process individual events with individual copies of your code. The difference is you get back a response immediately, right? There's no queuing construct in the middle. This is the pattern you will see us using when you're using an HTTP endpoint for mobile backends and SDKs. In the case of some of our state change services like AWS CloudFormation or others, it's the same model where you need a response back immediately. This is the model you would use. Of course, in this case, retry has to be taken care of by the client. If it's an API endpoint calling us, the API endpoint has to take care of retries. If it's your service calling it, it'll have to do retries because, well, we really don't know what happened after the function went on. The third one's interesting because this is kind of a mixed mode of other elements. This is when you're processing streaming data sources. So in the AWS world, the Kafka equivalent is a service we have called Amazon Kinesis. There's this concept called shards, which is basically a partition of an ordered partition of the data that's flowing in, right? So because it's an ordered partition, the order in which the events are processed on each partition or each shard is important. So the model that we have in the other cases where each function processes each event independently of any of the others doesn't work because you can't guarantee ordering in that particular model. So instead, what Lambda does is when you combine it with a streaming event source, it actually runs a copy of your code per shard or per partition over there. And what you can do is supply batches of events to each function to go and process, right? So basically in this case, if there were 10,000 events coming in on one end, they got partitioned across 5 shards, you can set up Lambda to say, read this particular event source at a batch of 50, which means each invoke will get a collection of 50 invokes from that function, processes it, and move forward. Now, this is also where we probably have a most aggressive retry policy in place. Again, going back to kind of that reliability construct, because streaming data processing, the data which is probably coming in is time series, is ordered, the guarantee matters of it getting processed. Lambda essentially does infinite retries till the time the data either expires or we get it right in order to kind of keep moving forward over there, right? So you will see this kind of pattern fitting in with, we have service companies like Localytics who do mobile analytics. They use this pattern for kind of building a big part of their data platform. And they're about, I want to say about like 400, 500 million events a day right now flowing through Kinesis and Lambda together, right? So 3 different kind of scaling behaviors, but all of them kind of giving you the same guarantees and constructs, which is it'll automatically handle spin up as many copies of your code as required for the events coming in. And I'll specifically call out this one thing because it keeps coming up. We don't send more than one event to one copy of your function at a given time, all right? A function may process another event another time, but if 100 of them show up at the same time, there will be 100 copies of your function running, right? So there's no concept of a per instance concurrency, so to speak, that's happening over there, all right? So, Shawn.
All right. To touch upon a point that Ajay touched on, at Uber with a microservices model, one of the challenges we have is the following. Our biggest day ever, every year, is Halloween. And then our biggest day ever, every year, is New Year's Eve. So we do a capacity planning exercise here at Uber. Now imagine you have a large number of microservices. How do you do capacity planning? Well, you go to every developer who owns every microservice and you say, hey, can you do some back of the envelope math of how much capacity you think you're going to need on New Year's Eve this year? And each of those developers does some math and you add them all up and that's the amount of servers you need and the services you need and stuff like this. I think we can all recognize that is not an optimal planning model because that assumes maximum load across a bunch of services versus aggregate load across the whole system. One of the beauties of a serverless system for a company like Uber or any companies using AWS is that you get to move from a sort of a peak capacity model to an aggregate capacity model. So the question you can ask yourself is, what is the total aggregate increase in load that we have across all of our systems for a peak event versus the sum of the aggregate load of peak of all those systems? It's a much easier way to plan for. It's much more cost effective, and it makes developers' lives a lot easier. So scaling is important. One of the promises that we've made for Catalyst is that we can do auto scaling so that developers just put their code into the system and then go have fun on New Year's Eve and don't have to sit around wondering if their page is going to go off. So today, since Catalyst is new, we have a manual scaling model, which is developers just can tell us how many instances they want to run. Believe it or not, this is actually a big improvement over the way the system works right now. There's a bunch of hoops you have to jump through right now at Uber to increase your pool size with containers. So we're going to make that a little bit easier, but this is just because we're brand new. What we're teaching the system is essentially a generic concept of scaling, which is for a given set of handlers, do I need to scale these things up or down? And that what we want to do is have a pluggable set of heuristics for letting those handlers decide whether or not they need to scale. For example, some things are CPU bound and you want them to scale when CPU usage is high. Some things are memory bound, you want them to scale when memory usage is high. Some things are bound by other criteria, such as anything that's reading from a log of any kind, be it Kafka or any other sort of streaming thing. You want to know how far behind you are, for example. So that may be another reason that you would want to scale up. So we're looking at doing that, and then we're going to make sure that we use metrics as a feedback loop. Because we have a system that we control, I mentioned that we wanted a little bit more control of the overall system. We're looking at doing some innovative things like the following. When we think that a scale-up might be useful for a set of handlers, we can actually do a canary scale-up to see if adding n instances decreased the overall load on the other instances by the expected amount. There's lots of times when scaling up won't help you, and I'll give you an example. If you're processing Kafka feeds, Kafka has a head-of-line blocking problem, which means that you can't move the zookeeper pointer from consuming a message to the next one until it's successfully consumed. Scaling out doesn't help you very much because most of your instances are just waiting. So that's a reason why you might not want to scale up, and we can teach our system, have our system know about those sorts of issues in a very composable way. Metrics and logging.
So we'll kind of come to the fun part of serverless. Right now, you've got a bunch of functions running, talking about events and requests to each other's. What about debugging comes the question most commonly, right? You don't have a server sitting around that's actually creating streams of data or logs that you can go dive into. There's no machine to SSH into to go and figure out what's happening over there. And it is interesting, like when we started out with this, we said, okay, let's start with the basic. We'll go with printf debugging, like anything that you put in your code and you write, log or print, automatically gets piped into a service that we have called CloudWatch Logs that aggregates all the logs from all the instances of all your functions that are running and gives you a partition view of them, allows you to search, find explicit records or entries that you're looking for, pipe it into an elk stack and create custom visualizations. That's kind of the default debugging story that's in place today. We're looking at kind of ways to make it stronger and better. I'll kind of talk about one of those. But that's kind of the story today. And surprisingly, that's actually worked out really nicely for many of the folks to start with, right? Like saying that now, when you start hitting 500 billion transactions a day, log diving becomes its own problem. We recognize that, and there's a solution that we have for it. But again, the basic construct of having each function say what's going on with it kind of works out really well. Lambda also offers kind of 4 metrics out of the box as to what your function is doing most commonly. So the number of invokes it's receiving, how long each function runs, because remember, you pay for how long your function runs, so you probably care about looking at that number. If it's hitting any kind of throttles, there's sort of a soft limit on the overall account, which kind of allows you to do for kind of preventing runaways. But if you're hitting throttles, you'll get to know that. And of course, any errors that are happening in your functions. The logs that you create allow you to also create custom metrics using the CloudWatch metrics capability. We also have sort of partnered with a lot of our AWS ecosystem partners around, Loggly, Splunk, Sumo Logic, Datadog, who can siphon any of these activity logs that you have inside your functions and put it in their individual dashboards as well. Now, these all help you with individual functions, but what about kind of the overall app? So one of the capabilities that we've been working on, and this is coming soon, we announced this at reInvent last year, is this new service called AWS X-Ray that allows you to do essentially request tracing across the stack of your serverless app. So you can actually trace a request from the API endpoint to the function that it calls, double-click into your function and see how much was spent in service overhead versus your code versus the call to, say, DynamoDB versus the call to your HTTP endpoint, and all the way back out, right? So you get kind of 2 elements for it. One is kind of this circle diagram on the side, which kind of gives you the service map visualization. So it gives you the actual hot paths within your application, seeing how much traffic is going through different elements or different elements of your function. It also kind of gives you the breakdown of what individual function calls look like. So it gives you kind of really precise and deep insights into kind of fine-tuning the latency and kind of error rate of your function, which both then count back into how efficiently you're writing your code, how you can optimize it across for different event sources and otherwise. And this is not out in prod yet, but I promise you it's in the works. But kind of you can the strategy that we're taking for debugging is logs and metrics for individual functions, services like X-ray to kind of give you service maps and utilization and elements over there. Local debugging comes in and out for us in various forms and fashion. We found people kind of really happy with what we do with our IDE tools, but there's always more we can do. We have had kind of partners build out Docker-based solutions for simulating the Lambda environment, kind of trying to do local testing over there. You'll kind of continue to see more investments in that kind of particular area. And I think Catalyst kind of builds out a similar model for you guys, right?
Yeah, exactly. We do similar stuff, but based on Uber's infrastructure. So Uber has its own metric system. It's called M3. And we report metrics into M3. M3 is very similar to StatsD if you've ever used StatsD. What's cool about the way Catalyst works is that we inject quite a lot of metrics about what's happening with your handlers automatically for you. Latency, calls, successes, failures, QPS, timings, both in terms of the end-to-end time for your function. We also return like how much time the Catalyst overhead is. So we track how much time we've added to your invocations. Right now it's very small. And then what we do with that information is we have templated dashboards that allow developers, if they write a handler on our system, to just be able to look at a dashboard that has a ton of information for them for free. They can then customize that dashboard for their needs. But we want to make sure that out of the box, we give folks as much facilities as we can so they can just focus on their business logic. Here at Uber, we have a system called Jaeger. The little graphs that Ajay showed with X-ray, Jaeger is very similar. Jaeger is a derivation of Zipkin that came out of Twitter. So we've built a lot of tracing around that. As a microservices-based company, tracing becomes a big deal about how you follow a request through a bunch of services and make that into a sane thing that developers can debug. For logs, we use ELK as well. So when services produce logs, they automatically get pushed into ELK clusters here at Uber. So that all hangs together, but they're still disparate services. So a lot of times the conversation that we would have here in Uber is, well, why are you guys doing X? Because there's already an auto-scaling service. There's already ELK. And we want to make sure we sit on top of those. But one of the challenges that we have is that developers have to learn how to use each of these individual systems and where they are and remember the documentation for them. We want to give them a very simple experience that spans all these services. When they discover they need more customized logging or they need more customized tracing, then they can learn about those services and use them directly. But we want to be a nice facade across a variety of things. So here's an example of a dashboard that we emit automatically. Ben's going to show you a Kafka example here in a second. I showed you some Kafka code earlier on, and this is the sort of information that we generate automatically from Kafka, or from any handler, but specifically for Kafka. So you can see here that we generate CPU usage. It says context switches here, so we check the number of context switches, which is often a cue for whether or not you're I/O bound or CPU bound. Number of threads, memory usage, and how many consumers you have. So this all comes for free. You can see there's some drop downs at the top where a developer just types in their project name and they get this automatically. For Kafka, we do some specific things as well. We generate some metrics around the number of requests per second, the latency at P99 and P50 here, and latency average. The point is that we give people a lot of information for free that they can just use and then customize as they need. A lot of times developers won't even need to customize this because this gives them the basics. Developers care a lot less about dashboards than they care about alerting. And the alerting also comes out of the M3 system. So there's already metrics ready for them to build alerts around. So it's pretty cool. All right. You guys have probably had enough of us talking. So you guys want to go first?
Yeah.
What's it? How about you go first?
All right.
So my name is Brian Liston, developer advocate for serverless at Amazon. That includes Lambda and API Gateway. This is Rory Jacob over here. He's an engineer on the Lambda team. If we can get our screens up here in a second. Perfect. So one of the questions that we get often is, how do I do continuous integration, continuous deployment with Lambda? And today we're going to talk about that. We're about to open source this new framework that we demoed at reInvent last year. If Rory can scroll down. This GitHub repository contains multiple steps, contains some CloudFormation templates, some SAM templates that we'll get into. But basically, this application is a full serverless website hosted by S3, API Gateway, and Lambda. So if we go ahead and jump over to the page real quick, we'll show them what's happening on the page, which right now is not a lot. So we see Sam floating around in space, just having a good time by himself. And we've already gone ahead and created the first couple steps here, so we didn't have to wait around. So if we go and jump into the pipeline, Rory will show you what the pipeline looks like today. So from source, we're actually pulling from a GitHub repository where we've got our application checked into. Our build stage will run on code build and do npm install. We'll go through our build spec and show you exactly what's going to happen during that build process. And then from there, it's going to create a CloudFormation change set and do a deployment on CloudFormation. So if we go ahead and let's go ahead and make the change in the repository real quickly. So this is the repo right now for the application. So Rory's going to go into the index file here, and we're going to modify how many SAMs there are on the screen. So today there's one. So Rory's just going to edit this right in the GitHub editor. And then he's going to go ahead and commit that change. And then if we go back over to the code pipeline for a minute, we'll let this sit here for a couple seconds. This should pick up the change and initiate our build. Once we see that change pick up, we'll go ahead and jump over and we'll jump back and show you what's happening in our build spec. Which usually takes about 20 to 30 seconds. There we go. So it's in progress. It's going to go to GitHub. It's going to pull down the latest code. So if we go back to the repository real quickly, and we go ahead and take a look at the build spec. So this build spec is telling code build exactly what to do, right? So we're doing an npm install. So we're grabbing any modules that are in the package.json specified for the application. This application is specifically written in Node.js. And then we're doing an AWS CloudFormation package, which essentially creates our SAML for us. And our artifacts generated are our SAML file and our staging beta.json. And if Rory wants to show what the SAML looks like. So this is our basic SAML. You saw a little bit of this when Ajay was doing his demo earlier. It looks very similar. It's got a basic serverless function with an individual code URI, which is just the local files. And then we've got the reference for the multipliers and the origin URLs. We'll talk about those in a little bit. Those refer to our environment variables. If we go to the Lambda management console right now, we can see that we've already deployed this at one point. So we can go ahead and go into that function. And if we go to the monitoring tab, you'll see that there's already invocations happening. So that website in the background, which is running in S3, no servers, it's constantly hitting an API gateway endpoint to get how many SAMs are supposed to be displayed. So it's just doing essentially, an AJAX call to API gateway. So if we look back to code pipelines and we're still in the build process, this can take anywhere from 1 to 5 minutes right now.
So I think one interesting thing to call out at this point is all of these operations that are being automated using code pipeline or code build are all doable through the CLI, right? The individual deploy, the individual package. What code pipeline is basically giving you is orchestration of your build pipeline to kind of turn it into a CI/CD solution. But everything that you see through the management console for seeing monitoring or kind of doing deploys or test invokes or anything that you're seeing through this automation system is available through APIs and CLIs as well, which is available for Lambda. If you want to go ahead and go to the API gateway console for a second, we'll show them that staging URL. So you can see here, Rory's got a couple APIs already deployed. This one specifically SAM around the world. We'll go to the prod stage. And so this URL is specifically what the S3 website is hitting. So if Rory clicks on this right now, he should hopefully still get a 1 unless we've already finished deploying, which we haven't. So we're still getting a 1. Once the code build finishes deploying, we should get a 15. And we should get more SAMs.
Yes, as people know, demos tend to go slower than they should. So why don't we jump over to the Lambda function real quick and look at the actual code. So slightly different than what AJ showed earlier. AJ showed a standard Python application for Lambda. This is a Node.js, standard JavaScript, nothing special. If we scroll back up to the handler real quick, you can see here we've got the export handler with the event and the context, very similar to Python where we take in the event. And then specifically, yeah, and Node, we have a callback. So there's a couple things to call out on here. We call them out in the actual documentation in the GitHub repository, but we specifically send headers to allow cores, so basically cross-site requests from the S3 bucket to the API gateway endpoint. Let's go ahead and check that. So, all right, so the change set's finished. So now if we go look, if we were to click on that and go to CloudFormation, we would see that it's deploying. And now we have more than one SAM. So another interesting thing to go do, if we go back to the Lambda function now, and we refresh the Lambda function, we should see that we have a SAM count of 15 inside the function. Now there's another thing that we can do real quickly. If we scroll down, we can take advantage of our environment variables. So this is something you might do in a typical dev environment when you're doing testing and you might want to increase load or send config variables. So we've got a SAM multiplier here and we can say, let's do 10 or 20. And then Rory's just gonna hit save. And then he's gonna go back over to the website and maybe he'll pull up the dictionary. And they should get multiplied. And we didn't have to wait for any code deployments. We didn't have to do anything, just temporary config change via environment variables. So this code is publicly available now. You'll be seeing a blog post probably early next week, along with a screencast on how to do this. Send us your feedback. And we'll be around if you have any questions afterwards.
All right, pretty awesome. Good stuff. I feel like I'm visualizing infinity. Okay, awesome. Okay, Ben's going to give a local, sort of a demo of Catalyst, both locally and into production as well. So you ready to go? Microphone holder? Yes. Okay, I'll be your microphone holder.
So I'm Ben. I'm on the Catalyst team. I had the privilege to work on this. It's a really interesting problem. I think it's one of the most interesting problems I've worked on in my career. And just figuring out how to wire all these things up and make them respond and create a great user experience has been really fun. So I think one of the things that really distinguishes Catalyst is that we built it from the ground up to really consider the user experience. So I'm going to show you some of those things and show you how we made it really, really easy to test your handlers and how to make them react really well to event handlers. So the first thing I want to show you is this is just like the handler that Shawn showed you during the demo, during his talk. So you can see here we have HTTP handler. And this HTTP handler, it's the same code. So I've scaffolded a project here. So that means that I've run a tool that basically generated this project. So this gave me some boilerplate code. And this is all the code that it took to stand up an HTTP handler. So really simple code. And this is Go. So just to walk you through this, if you've never seen Go, this top section is the import. So this kind of says which libraries I'm using. So in this case, I'm importing Catalyst and I'm importing HTTP support. And I'm also importing the Go's built-in HTTP support. And then I have a function here. So this is the Lambda that I actually want to run. In this case, all it's doing is just writing some bytes out. In this case, it's like a header that's a smiley face. And this last piece is how I register my function. So this is the piece that tells Catalyst how to invoke this code. So I'm telling it to run this function, and I'm telling it to run on /, which means just the default HTTP URL. I'm telling it to run on GET requests. So then just to give you an idea how easy this is, so I can go to my Catalyst. So this is the same thing I was just showing you. So let me move this down a little bit. So I'm in that same directory. So if I count my handlers, you can see this is the code I was just showing you. And then all I have to do is say Catalyst run. And Catalyst already knows how to invoke this thing. So it's literally going to start up an HTTP server, and it's going to start running this code locally. So this is the same directory I was just showing you. Catalyst is aware of where you are with its command line tools. So that's one of the things that makes it really easy is even when you're working in a huge project, Catalyst is totally context sensitive. So if I say Catalyst run, it's going to run this HTTP example. So I'll do that. So again, this is actually going to build my code locally, compile it for my system. It's going to start up an HTTP server, and then that will be listening, and I can use all the same HTTP tools I would use. So I can use curl, I can use a web browser, I can use HTTP testing tools. Everything works because it's just standard HTTP. So I'm going to use Chrome, and I'll pop over here, and then when I make a request to my local host, then I see that smiley face, which is what I expect. And just to show you the source, that's the H1, the header, and it's smiley face. And just to give you an idea how easy it is to edit, I'm going to change this to something else. So I can say like, hello, Serverless Meetup. And then I just come back over here and I say Catalyst run. And now it's gonna run the new version of my code locally. And so again, it's building the code. It's gonna restart the HTTP server. And then when I come to Chrome and refresh, now I have my new code. So you can see, I was able to rev on my code within a few seconds, which is a really easy way to test things and to make a lot of progress and iterate on your code. So not only is it really easy to do local development, and it's actually very easy to do remote development. So let's say I've decided my code is good, then I'm actually able to upload it into production. So to give you an idea, I'm actually going to switch to the Kafka example, where we can consume a Kafka feed. And I'll show you the code for that. Again, it's very similar to the code you saw during Shawn's talk. So we have the same structure here. We have our imports that says which libraries we use. We have our function that we're going to run. So this is the Kafka function. It's going to take a byte array in, and it's going to just log something. And then we're registering this with the Catalyst system. So we're saying, I want you to run my Kafka handler function on this Kafka topic, and use this consumer group in these clusters. And then you'll be able to test this locally. And so I'm actually going to upload this code to the Catalyst system. So this is, again, doing a build. And this is actually a cross-compile build. So this is going to build it for the remote Catalyst system, which is Linux in our case. So it's actually building a Linux binary. And then it's going to upload that tarball up to the Catalyst system. Demo. And actually need to, in order to connect to production, we need to have this, this little thing that makes that possible. I'll try that one more time. And this time it should connect to Catalyst and upload our binary. So you can see it successfully updated our binary. So this is the git SHA of our commit. So now this git SHA is available to deploy. So I can tell Catalyst that I want to run this code, and I want to run it in the dev stage, and I want to run it with one instance. So I'm going to ask it for that, and then it's going to say, okay, so you want to deploy one instance, and I'm going to confirm that. And now it's going to actually initiate that deployment. And then I can do Catalyst status, so I can check on that and see. Now you can see that Catalyst is showing me that I have one box deployed running this SHA that I told it. So that's great, so it's running. And we have built-in metrics, so I can actually come over here to our dashboarding system. It's called Grafana. And then I can wait a little bit here, and then we'll start to see the metrics flowing in. You can already see our first data point. So here's that one Kafka consumer. I can see how many messages this is handling. So it's handling approximately 5,000 messages every 1 second. And I can see the handler latency. And I think one thing that I'm really proud of is the latency of our system is very low. So you can see our average handler latency is tiny, and the overhead that we're introducing is very small. It's kind of like nanosecond level overhead, which means that you can get a lot of work done with just a few boxes. So as this data starts to trickle in, we can see we're getting more and more metrics here. And so then I can actually show, if I wanted to scale up, I can do that really easily too. So I'm just going to come over here. I'm going to do another deployment. And this time I'm going to deploy 3 boxes. So Catalyst is telling me I'm going from 1 to 3, confirm that. So now I can do Catalyst status again. And we can see that Catalyst hasn't yet finished making my request. So if I keep doing this now, so now it has fulfilled my request. So now I have 3 boxes. And if I come back over here to my dashboards, it takes a few minutes to update, but you can already see it's starting to start up some workers and they're starting to consume messages. And there we go. So now it's popped up to 3 workers and they're all reporting metrics and all consuming messages. So just to give you an idea, this is, I now have a production scale service running my ingesting these Kafka streams. And this is a lot of services at Uber do just this. And maybe they do some billing for trips. They generate an email when you take an Uber trip. So they would hang off a trip stream in Kafka. And then every time there's a trip, they send you a receipt. So you can imagine I would dump some emailing code in my handler and I call it a day. And that's amazing because it takes so much more time than that today to have that service running. So that's Catalyst.
Awesome. Thanks, Ben. All right. Awesome. So wrap up. It's not just a fad. Serverless is here to stay. We think it has a lot of promise in the future. It allows clear separation of infrastructure from business logic. I think both the demos we saw here, you don't have to know anything about the basics of containers or how deployments work or any of that stuff to get code out into production. It's a very consistent programming model. The programming model that we used for the SAM, multi-SAM animation demo and Kafka and HTTP, all pretty much the same. It's concepts that developers can learn once and reuse in many places. And then it's a common tooling experience across multiple systems. So those are all big wins. I want to thank everybody who came out tonight. I want to thank the Catalyst team, the team that we're hiring. Amazingly strong team doing really cool work. And I'll hand over to Ajay for some closing thoughts. But thanks everybody for coming out tonight.
Thanks, Shawn. Thanks for the sort of opportunity. And I think just one probably last comment I'll leave is, when we started our Lambda, there was a little bit of sort of apprehension when we put it out there, right? It was kind of a new model. We had a few people in AWS using it. We put it out there saying, we'll see how it goes. And today we have, 3 months ago, we had companies like Coca-Cola, Capital One, iRobot, Localytics, all on stage saying, we're basically heading towards 100% serverless for their stacks, right? And these are not companies you would traditionally consider sort of forefront of IT, but even for them, kind of, so many of them are sort of taken to leapfrogging the conventional element that comes with it. So there's a lot more that has to be done over here. Like there's the deployment tooling, and there's debugging, there's the novelty of the model that's being come out over there, but super kind of valuable feedback from the development community such as you. So keep telling us sort of what you want to hear more or what you want to see different in Lambda and Catalyst and others. And hey, if you want to solve some of these problems, we're hiring too. All right. Thank you, folks. Yeah.
Any questions? Well, let's see if we get any from the general group. So we'll handle a couple questions here and then we'll break so people can get snacks and drinks and stuff. And we'll break and do one-on-one afterwards, definitely. Question here. So the question is, how do we handle business or application level metrics? The same way you do today for our system. You can emit any metrics you want into the same M3 system. We emit standard Catalyst formatted metrics, but you can emit anything else you want. And so that would work exactly the same.
Lambda, similar model. Basically, the metrics that you emit into CloudWatch can be namespace. So depending on how you name your functions and others, you can kind of do it that way. There's a capability called tagging within AWS that allows you to tag resources in other places. Once we add that into Lambda and API Gateway, you'll also be able to see metrics by tags, so to speak. So all the invoke metrics or streaming metrics, et cetera, you'll be able to see in one place.
Let's take 2 more questions. Great. So the question was, what are we doing in terms of a container format in our systems? And how are we taking advantage of the various container orchestration systems that are out there today? So here at Uber, the way that things work is that you publish your code and there's a containerization service that takes your code and runs some scripts that you put in your repo and generates containers. Catalyst does that for us. The way that it works in terms of Catalyst from a user point of view is that Catalyst is going to roll out that standard Catalyst container, and then we'll download the user's bits on demand once the controller says which manifest it's handling. So in terms of orchestration at Uber, the underlying system here is Mesos Aurora. And we have a very thin dependency on Mesos today, which is we just need to get instances from Mesos so we have a warming pool. It's basically how it works for us. It's Docker.
we use a variant of LXC for running the container tech for Lambda. The scheduling and placement algorithm is custom. You can imagine that a lot of our sort of secret sauce and kind of coolness in terms of scaling actually comes for that. So there's a bunch of optimizations we have had to do at that level, which requires us to build our own. So depends what you mean by crossover. I mean, obviously we're in the same kind of family, so that we have a lot of container tech sharing that's happening over there. If you're specifically asking, is Lambda built on ECS? We can talk about it after, but I'll give you a hint. Both of them launched at the same time, so they kind of grew up together, so to speak. But in terms of what is it? You asked probably one more question.
All right, one more question. So I'll handle that. The question is, does Catalyst support auto-scaling? Today we have a manual method just because we're really early, but we absolutely intend to support auto-scaling based on metrics out of the system, whether it's CPU or memory or so request pressure, lots of different ways we can do auto-scaling, but we will absolutely support it. Developers shouldn't have to do anything in the standard case.
Oh, sure. So the question was sort of what's the disadvantage when you compare serverless with non-this thing? Disadvantage is a heavy word because it implies that it's something negative. The way I like to talk about it is serverless is not for everything, but for a lot. There is going to be something like the fact that serverless has that kind of opinionated structure about saying things need to be event-driven, things need to be written in a stateless fashion, things to be written in a modular fashion, means there are certain applications and you can't customize the environment, right? Means there are certain class of applications that will never ever run serverlessly, right? Don't talk about deploying Mongo serverlessly or deploying a Salesforce application serverlessly or any on. So those kind of constructs just don't apply. If you want to go at custom hardware requirements, you're running a game rendering engine and you need a specific SKU of CPU to actually render that, you're not going to get that through serverless because that area is completely abstracted for you, right? The other element I would actually kind of also throw in over there is it requires you to adopt that kind of programming model that we talked about, right? You're kind of you can't take a WAR file that's running on Apache today, pick it up and drop it into Lambda. I mean, you could. I probably won't advise you do it, but that's not the right model for you to do it, right? So there's there's kind of a little bit of a mind shift that you need to go through to kind of switch over there, right? And third, I'll kind of call out is there is areas where the control of the infrastructure differentiates your business, right? And I'll kind of call that explicitly. If you think that control of the box, maybe for compliance reasons, maybe for regulatory reasons, maybe for reasons that your hardware is the one that's actually differentiating you, serverless doesn't give you that, right? The hardware is controlled by the provider, the SKU is controlled by a provider, you're dealing only with the resources. So those kind of applications which you would build with servers today will probably not be a good fit for what you would do with serverless. But for everything else, probably the last one I'll call out, and it's temporary, but there are limits to what Lambda applies, right? So today we have a 5-minute cap on how long a function can run, right? There's a cap on how much memory and CPU you can allocate to your function at 1.5 gigs. I call those out as that I'm not as sort of fixated upon because you can imagine those will always be limits are meant to be raised. That those will always probably go up, but the other elements though are going to be kind of pretty standard lines for you to think about. So the way we think about it is you're always going to have that spectrum of sort of VMs, containers, and functions as your compute environment, and you're going to choose one of those for your applications depending on kind of your level of control that you desire, your level of comfort with the model, and kind of your level of operational effort that you're willing to put for the trade-off that you have over there. So.
That's a great question to end on. Thanks for asking that question. Thanks everybody tonight. We'll be available for questions after. Thanks.